Are you tired of formulas in physics textbooks? Or learning English just through grammar rules? Well, how about combining these two worlds and breaking the boundaries? We are embarking on an exciting 8-month journey where science meets language. Welcome to our ET Winning Project, fun with physics, games, experiments, and discoveries. This project brings together curious students aged 13 to 18 and creative teachers from all over Europe. Our goal is very clear: to break down the walls between physics and English classes. Our project is built upon 4 strong pillars. First, we bring theory to life through hands-on and fun learning. Second, thanks to active language integration, we learn English naturally and experientially while sharing our observations and ideas. Third, we polish our core skills such as teamwork, critical thinking, and problem solving. And finally, we establish curiosity-driven communication. Because the best learning starts with curiosity. So, what adventures await us on this extraordinary journey? Here are the wonderful themes we will explore through unconventional and fun approaches. We will solve the mystery of light and shadows with the Shadow Play Lab. We will learn Newton's laws of motion, thrust, and momentum by racing with the balloon rocket race. We will witness the dance of potential and kinetic energy with gravity in our marble roller coaster project. We will examine pressure, buoyancy, and density with water park physics. We will discover air resistance and aerodynamics by saying, "Fly with science." And finally, we will light up our world with electric circuits, conductors, and insulators by saying, "Light up your imagination." The adventure begins. 1. The Shadow Play Lab. Light and shadows. Through English storytelling using past tense and positional words, students explain linear light travel, analyze shadow formation, and explore transparent, translucent, and opaque materials.
We used a small light source to create sharp shadows.
Then we used the white light source to make them soft and blurry.
Hello, today I will talk about light and shadow. A shadow is a dark shape that appears when an object blocks the light. When light cannot pass through an object, a shadow is formed on the ground or on a wall. To give an example from everyday life, when there is a sun during the day, the length and location of the shadow changes according to the movement of light. There is a shadow game played behind the curtain in our country. It's called Hacivat and Karagöz. Thanks for listening.
Hello! In this project, I wanted to demonstrate the properties of shadow through shadow art. To do this, I created a Atatürk figure using opaque objects, paper and cardboard. So what is a shadow? When light from a light source hits an object, the darkness that forms on the opposite side of the illuminated object is called a shadow. The light rays from the light source follow a linear path. If we look at the difference between translucent and opaque, like this, my finger's shadow becomes darker. As you can see, the farther an object is from the light source, the smaller its shadow becomes. If the distance between the light source and the object decreases, the shadow becomes larger. Thank you for listening to me.
Hi eTuning family. We are gonna explain what is the shadow through shadow play. Firstly, we have a toy. We will use it for opaque object. If you wanna have a shadow, you need absolutely an opaque object. When we bring it closer to the light, the shadow gets bigger. When we move it farther away, the shadow gets smaller, like this. In the past time, people used their hands for shadow play, like this and like this. It's a dog, and it's a bird. Yes, and it's a wolf.
Hello, we are the team from Romania. Today we will show you how we use the fed up at physics. For example, today we will show you how we get the white color. White light can also be obtained by mixing three primary colors, red, green, and blue, which combined are perceived by the human eye as white. Determine what colors the person sees for various combinations of red, green, and blue light. Describe the color of light that is able to pass through different colored filters.
Two, balloon rocket race. Newton's laws of motion. Thrust, momentum. Students explore action-reaction, thrust, and momentum through experiments, practicing predictions, result comparisons, and completing English lab forms.
Wait for it, steady, and blast off. Look at that go. How does a plastic bottle fly like a real rocket? The secret is momentum. It's the product of mass and velocity. Before launching, we pump air into the bottle. This creates immense pressure inside. At this stage, the total momentum of our system is zero because nothing is moving yet. The moment we release the trigger, the pressure forces the water out at high velocity. According to the law of conservation of momentum, the system must stay balanced. If the water gains momentum downwards, the rocket must gain equal momentum upwards. This is Newton's third law in action. Every action has an equal and opposite reaction. Water goes down, rocket goes up. Science is truly amazing. Now, go build your own.
Momentum is the product of mass and velocity. P equals m times v. It shows how much motion an object has. Objects with larger mass or higher speed have greater momentum and are harder to stop. Momentum increases with the velocity and decreases when velocity decreases. In the push, equal and opposite forces act on both objects. These forces change the velocity, so their momenta change. The stronger the force, the greater the change in motion. This demonstrates that momentum changes when a force is applied.
When we drop this ball, they don't go very high. So how can we make them go as high as possible? When we stake the balls like this, they will gain speed as they fall, meaning they will have momentum.
After the basketball hits the ground, it will transfer its momentum to the falling tennis ball, thus launching it even higher.
Hi everyone, watch this experiment.
This is a simple balloon, but something interesting is about to happen.
Pay attention when we let it go.
The air rushes out this way.
And the balloon moves the opposite way.
This is Newton's third law. For every action, there is an equal and opposite reaction. The action is the air going backward, and the reaction is the balloon moving forward. This is the same principle rockets use in space.
Hello everyone! Today we will show you a very beautiful experiment. We need tape, scissors, a straw, string and a balloon.
Step 1. Thread the string. Step 2. Inflate the balloon. Step 3. Tape it to the straw. Why does it work? Because of momentum. The air has mass and velocity, and it transfers its momentum to our rocket.
Hello everyone, welcome to the Earth-winning science activity. Today we are exploring Newton's third law of motion, action and reaction. First, let's observe what happens when I pull the card slowly. As you can see, the coin moves together with the card because there isn't enough sudden force. The coin does not drop into the glass. Now let's reset the setup and try the real experiment. When I apply a sudden and quick force by flick the card, it flies forward rapidly. Due to inertia, the coin drops directly into the glass and hits the bottom. This instant impact perfectly demonstrates the principle of action and reaction working together. Thank you for watching.
Hello everyone! Today I'm going to show you a simple experiment that explains linear momentum and impulse, which are closely related to Newton's laws of motion. Momentum describes how much motion an object has. It depends on the mass of the object and its velocity. In this experiment, I will drop an egg from the same height onto two different surfaces, a hard surface and a soft one. Even though the egg starts with the same momentum in both cases, the outcome will be very different. First, let's see the egg falling onto the hard surface. When the egg hits the ground, it stops almost instantly. Because the stopping time is extremely short, the force acting on the egg becomes very large. According to Newton's second law, a large change in momentum over a very short time results in a large force, which causes the egg to break. Now, let's see the soft surface. When the egg lands on the soft surface, the pillow compresses and increases the time of the collision. The egg still loses the same momentum, but it does so over a longer period of time. This is explained by the concept of impulse, which connects force, time, and the change in momentum. Because the collision time is longer, the force acting on the egg is smaller, so the egg does not break. This principle is used in many real-life safety designs, such as airbags, helmets, and protective packaging, all of which increase the time of impact to reduce the force.
Hello, today we are presenting our work on Newton's lens, developed by Isaac Newton, one of the most important figures in physics. This lens explains how objects move and how forces act upon them in our daily lives. During this presentation, we will explain each law and share simple experiments to demonstrate these concepts in practice, showing how physics is part of our everyday world.
First, Newton's law of inertia. Newton's first law states that an object remains at rest or continues to move with constant velocity in a straight line unless a resultant force acts upon it and change its states of motion. This means that objects tend to resist change in their motion. This property is called inertia and depends on the object's mass. The greater the mass, the greater the inertia. Second Newton's law, fundamental law of dynamics. Newton's second law states that the acceleration of an object is directly proportional to the resultant force applied to it and inversely proportional to its mass. F equal m plus a. In this equation, F represents force, m represents mass, and a represents acceleration. Therefore, for the same applied force, an object with a greater mass will experience a smaller acceleration. Third Newton's law, law of action and reaction. Newton's third law states that for every action there is an equal and opposite reaction. When one object exerts a force on another object, the second object simultaneously exerts a force of equal magnitude and opposite direction on the first object.
In this experiment, you put a piece of card on top of a glass and a coin on top of the card. When you give the card a fast flick with your finger, the card flies away, but the coin stays in the same place because of inertia. Because you move the card so fast, the friction, the rubbing force, between the card and the coin only lasts for a split second. This means the card cannot pull the coin along with it, so the coin stays in the air for a moment and then gravity makes it fall straight down into the glass. This experiment shows Newton's first law of motion. An object stays still unless a force makes it to move. In this case, the coin wants to stay still until gravity pulls it down.
How we show in this short video.
In this experiment, you push an empty toy car and then you push the same car loaded with several heavy books. You will see that the empty car moves and speeds up much faster than the heavy car. According to Newton's second law of motion, how fast something speeds up, acceleration, depends on two things: how hard you push it, the force, and how heavy it is, mass. If you push both cars with the exact same strength, the car with the books that has more mass, so it speeds up slower. The empty car has less mass, so it speeds up faster. This experiment proves the connection between force, mass, and acceleration, which we write as force equals mass multiplied by acceleration. In simple terms, the heavier the object, the harder it is to make it go fast. A water rocket works by shooting water out of its bottom opening at a very high speed. When the rocket pushes the water down, it applies a force to the water. According to Newton's third law of motion, the water pushes back on the rocket at the exact same time with the same amount of strength, but in the opposite direction. This backwards push reaction force shoots the water straight up into the air. The faster the water shoots out, the stronger the pushback will be and the higher the rocket will go. Because of this, a water rocket is a perfect example of the law of action and reaction. It shows that the force always comes in pair and push in opposite directions.
How we show in this short video. In conclusion, Newton's laws are fundamental for understanding the motion of objects and many phenomena that occur around us. During these experiments, we are able to observe in practice concepts such as inertia, the relationship between force and motion, and action-reaction. These laws are not only useful in school, but are also applied in areas such as transportation, engineering, sports, and even space exploration. Therefore, we can see that physics is very important because it helps explain how the world works and how the things we use every day
3.
function.
Marble roller coaster potential and kinetic energy, gravity, energy transformations. Students experiment with Newton's action-reaction law, thrust, and momentum, practicing predictions, comparing outcomes, and completing English experiment forms.
Hello everyone. Today I will explain kinetic energy using a roller coaster. In physics, kinetic energy is the energy an object has because of its motion. The formula for kinetic energy is kinetic energy equals 1/2 times mass times velocity squared. At the top of the roller coaster, the train moves very slowly, so its kinetic energy is low. Most of its energy is gravitational potential energy. As the roller coaster goes down the track, gravity causes it to accelerate. Its speed increases, and according to the formula, the kinetic energy also increases. At the bottom of the hill, the roller coaster reaches its maximum speed. Therefore, its kinetic energy becomes the greatest. As the train climbs the next hill, it slows down, and some kinetic energy changes back into potential energy.
Hello, I'm Leandro Brito. I'm 18 years old and I'm from São Pedro de Alva. And I'm from the 12th grade, and I'm about to show you my 12th grade project in the physics class. So, what we have here is basically what I call CLAU. In Portuguese, it would be like Centro de Levitação Acústica Ultrassonico. In English, it would be like Ultrasonic Acoustic Levitation Center. And this is basically what it sounds like. This is a device, a gadget, that through sound, through only sound, ultrasounds in this case, I'm able to levitate objects. In this case, I'm going to be levitating polyethylene spheres, and I'm about to show you how I can do that. I can just grab one here, find more or less where's the middle, and it just stays there. We can see that there's nothing like hanging it or anything. This is levitating objects, particles, using purely only sound. Nothing like magnets or air is being used on this video. I can explain it like what's happening here. Basically, we have here a bridge. It all starts with, this is an Arduino and this is a bridge. It all starts here with the Arduino. This is a thing that I plugged into my computer and that I programmed. What I put here was the generation of the wave. In this case, is an ultrasound. I'm using 40,000 hertz. I programmed the wave itself, the repetition of the wave, and then the amplification of the wave. Then these white cables are coming from the power source. The power source is this that I plug into the power supply. This is just some wires that I put here to use like alternative power sources. Then the power comes to the Arduino, the information goes to through these blue wires to the bridge, and then goes to the outputs to the transducers. What are the transducers? They are the most important parts of this system, perhaps. They are these tiny like round things. This is basically like a very special speaker with a very thin membrane that is able to produce very high frequency sounds. And these high frequency sounds is what we call ultrasounds. That is the type of sound that I'm using in this contraction. Basically, what's happening here on the science point of view, I made like a tiny drawing. Like sound behaves in the air like through different zones, compression zones and rarefaction zones. In Portuguese, it would be like zonas de compressão e zonas de rarefação. And this is basically what makes the wave, the sound wave that we hear. Because sound is a pressure wave, we have like the wave itself, and the spikes are the compression zones, and the down parts are the rarefaction zones. And this is what sound is in itself, like this is what's supposed to be an ear. And then these compression zones and the distance between them is what our ears will make from electric signals. They will make these distances and the compression zones into electric signals that will then be understood by our brain. This is basically like if we had like a sound wave with a normal frequency, this would be like a higher frequency, the type of frequency that we use in here, because higher the frequency, higher the power, basically. And this is like what would be like a very low frequency output. Basically, we have this, and what's happening here is when two compression zones, obviously, this is a lot very important. There's a lot of things like the alignment of the transducers and the distance of the bases, because this is not just a distance, it's like a multiple of half the wavelength. In Portuguese, it would be like, a distância será múltiplo de metade do comprimento de onda. And this basically works like where the sphere levitates, we have like it's surrounded by compression zones, and in the exact spot where it is, we have a very big rarefaction zone. Sometimes the opposite can happen, like the spot where it is a very dense in particle spot. So we pretty much have the compression zones where there is a lot of density and the rarefaction zones where there is almost like a very low density of air molecules. And the sphere, the polyethylene sphere, stays levitating right in the middle of a lot of very big compression zones. This is obviously all very meticulous and calculated through the alignment of the transducers, but it's basically this. We also can try to levitate easily more than one sphere. We can put here another, and we can put even more. I can show it on images in the screen for you if you want. I have already made several of these gadgets, although this is the most stable one because as you can see I can clearly move this around and they won't fall. But I have also made other versions of this gadget. I can show it on the screen for you. With each version has a different type of arrangement of transducers. But yeah, that's basically it. Just a little bit about my project and how science can be very interesting and very fun. I'm literally levitating objects using only sound. That for me is a very incredible thing because it shows that sound is not just something of our days, it's something that can be used for things and that can have power, and we can see its power on our everyday life objects. That's it. I hope you liked it. If you have any questions, you can feel free to ask, and that's it. Goodbye.
Hello, today we are exploring Maxwell's wheel to show how mechanical energy works. By winding the wheel, we store potential energy. When I release it, this energy turns into kinetic energy, making the wheel both fall and spin. Let's look at the simulation for more detail. In the simulation, I have kept all parameters constant to focus on the charts. In a frictionless environment, the motion never stops. Look at the energy chart. As the green potential energy decreases, the blue kinetic energy increases. The dashed lines show that the total energy stays exactly the same. Now with friction, heat energy is created and the wheel eventually stops. You can see the energy waves getting smaller as they turn into heat. This proves that energy is never lost, it just changes form, and the total energy is always conserved.
Hello everyone! Today we're exploring the transformation of energy. When I hold this paint tube high up, it has potential energy due to its height. At the moment I release it, this energy turns into movement, which is kinetic energy. In the first race, the tubes have the exact same weight. I'm releasing them and it's a tie! Since their weights are equal, the speed and kinetic energy they gained are also the same. In the second race, one of them is heavier. I'm releasing them and the heavier one wins. Because as weight increases, the potential energy at the top increases too. As it rolls down, this turns into greater kinetic energy and speed, winning the race. That's how simple the transformation of energy is.
Hello, today I am going to explain energy transformation to you through bowling and dominoes. Ball is in the air, it has potential energy, which converts into kinetic energy as it falls. When the ball hits the pins, an energy transfer occurs, knocking them down. In these videos, potential energy is applied to the dominoes with a finger, and the blocks transfer this force to one another. Thank you for listening to me.
4. Water park physics, pressure, buoyancy, density. Students use English conjunctions in a vlog to justify their observations on fluid pressure, buoyancy, and density.
Hello friends, today we are going to do the water park physics experiment, which focuses on density and buoyancy that I prepared for my physics class project. For this experiment, I will be using liquids with different densities that you can easily find at home, like water, vegetable oil, and dish soap. The densities of substances, meaning their mass per unit volume, are different from one another. Substances with higher density sink to the bottom, while those with lower density stay on top. Now it's time to put this theory into practice. We will add our liquids into our transparent cup one by one, and we'll see who wins the race between them. Are you ready for the liquid race? 3, 2, 1, here we go. First, I'm adding the dish soap, then the water, and finally the oil. As you can see, the liquids have formed an amazing tower based on their densities. The dish soap stayed at the very bottom and the oil stayed at the very top. Now I'm dropping a coin into the cup and placing a small paper boat at the very top. As you can notice, since the metal coin has a higher density, it sinks to the very bottom, while the paper boat floats at the top because its density is the lowest. With this experiment, we have very clearly seen how the difference in density affects the position of substances. Thanks for watching. See you in the next videos. Goodbye!
Hello everyone. Today I will talk about my experiment about liquid pressure and density. For this experiment, I used dish soap, water, and olive oil. I carefully poured the liquids into the same transparent container. After a few minutes, I observed that the liquids formed different layers. The dish soap stayed at the bottom, the water stayed in the middle, and the olive oil stayed at the top. This happened because the liquids have different densities. Liquids with higher density stay at the bottom, and liquids with lower density stay at the top. From this experiment, I learned that density is an important property of liquids and it can affect liquid pressure.
Hello everyone. Today I will be explaining the Cartesian diver experiment. The Cartesian diver experiment is a simple science experiment that demonstrates the relationship between pressure, density, and buoyancy. When a plastic bottle is squeezed, the pressure inside the water increases and the air inside the diver is compressed. As the volume of the air decreases, the diver's density increases, causing it to sink. When the pressure on the bottle is released, the air expands again. The diver's density decreases and it rises back to the surface due to the buoyant force. This experiment shows how liquid pressure and density affects the movement of projects. Thank you for listening to me.
Hello everyone. Today I'm going to show you the physics of density and buoyancy. Density is the amount of mass in a unit of volume. In short, heavy liquids sink, light liquids float. First, I am pouring honey. It has the highest density, so it stays at the bottom. Next, I add dish soap and then colored water. They have lower densities than honey. Finally, I add vegetable oil. Oil has the lowest density, so it floats at the very top. Look at these beautiful layers. They don't mix off because of their different densities. Now, let's test buoyancy. This coin is dense, so it sinks to the bottom, but this piece of paper floats on top. Thank you for watching.
Pressure is all around us in everyday life. Pressure depends on the area of contact.
A small surface creates higher pressure. High pressure can cause objects to break or pop.
5. Fly with science. Force, air resistance, aerodynamics. While experimenting with aerodynamics and flight stability, students explain force, air resistance, and balance using English instructions, steps, and opinions.
Air resistance is a force that acts against motion in the air.
Air resistance helps the kite stay in the air.
Hello everyone! Today I will show you the effect of air resistance using two simple sheets of paper. I have two identical sheets of paper here. One will stay flat and the other will be crumpled into a small ball. If I drop them from the same height at the same time, which one do you think will reach the ground first? As you can guess, the paper ball reaches the ground much faster, while the flat sheet falls slowly. This happens because of air resistance. The flat sheet has a larger surface area, so it experiences more resistance from the air. The crumpled paper ball has a smaller surface area, so it experiences less air resistance and falls faster. This experiment shows that the shape of an object affects how it moves through the air. Air resistance can slow down objects with larger surface areas, while objects with smaller surface areas can move more easily. Thanks for watching.
Hello, everyone. Today I am happy to explain how a kite flies using basic physics. A kite flies in the sky thanks to the balance of different forces. When the wind hits the surface of the kite, it creates a lifting force. This happens because the air moves faster over the top of the kite than underneath it. At the same time, air resistance and the tension of the string keep the kite stable. If the design is aerodynamic, the kite easily fights gravity and stays high in the air. Thank you so much for listening.
Today I will compare two paper airplanes. A dart airplane and a glider airplane. I'm throwing a dart-type airplane. I'm throwing a glider-type airplane. The dart airplane had a more aerodynamic design, so it flew farther.
Good morning, everyone. Today we're going to talk about aerodynamics and how it applies to our STEM racing project. Aerodynamics is the study of how air moves around objects. It is very important in things like cars, airplanes, and even sports. In simple terms, better aerodynamics means less air resistance and more speed.
When an object moves, air pushes against it. This force is called drag. The more drag there is, the slower the object becomes. So, engineers try to design shapes that cut through the air smoothly. There are two main ideas to remember. First, smooth shapes reduce drag. Second, sharp edges or rough surfaces increase drag. That's why race cars and airplanes have curved and streamlined designs.
In our STEM racing car, aerodynamics is one of the most important things. If our car has less drag, it can move faster along the track. So, when designing our car, we focus on making it as smooth and as streamlined as possible.
For example, we try to use a narrow front, avoid sharp edges, and keep the body smooth. These small changes can make a big difference in the final speed of the car.
To conclude, aerodynamics plays an important role in many fields.
By understanding how air works, we can design faster, more efficient, and better performing objects. Thank you.
One of the most fascinating rules of the universe is Bernoulli's principle. It starts with a simple fact: when air moves faster, its pressure drops. 1. As you can see in the video, when we blow between two candles, the air in the middle moves fast and its pressure drops. The higher pressure on the outside then pushes the flames toward each other. 2. Similarly, when we blow between two hanging papers, the air between them moves fast. This creates a low-pressure area, and the papers come together instead of moving apart. Physics is not boring, you just need to see the amazing balance behind the invisible air.
When air is blown between two balloons, they are pulled together instead of moving apart. This phenomenon is explained by Bernoulli's principle. When air is blown between them, its speed increases, which causes the pressure to drop. Because the pressure between the balloons is low, the higher outside pressure pushes them toward each other. Thank you for watching.
Six, light up your imagination. Electric circuits, conductors, and insulators. Students build circuits, identify components, compare series and parallel configurations, and test conductivity, explaining their designs through an English video or poster.
Electric circuits are everywhere in our house. These lights work because an electric circuit.
When the circuit is open, electricity stops flowing.
When the circuit is closed, the lights turn on.
Hello guys, today I will explain to you how the electric circuits works. Here is an electric circuit that I set up. The black cable represents the negative cable. The red one represents the positive cable. A simple electrical circuit consists of basic elements such as power supply, conductor cable, control switch, light bulb, and hoarder. First, we tie up the positive cable that comes out of the power supply to the hoarder. Then, we tie up the negative cable to the control switch. After that, we tie up the extra negative cables one side to the hoarder. Then, we tie up the negative cables other side to the control switch too. And then, you're all done. You have an electrical circuit. When I open the control switch, the light bulb lights up. When I turn off the control switch, the light bulb goes out. Thank you so much for listening and see you soon. Goodbye.
Hello everyone, today I'm going to explain how police car LED lights work by building a model. For this project, we will need 2 blue and 2 red lights, 1 Arduino, a breadboard, a USB cable, 220 ohm resistors, Ampere wires. First, the Arduino is connected to the GND and the other end is connected to the negative rail. Then the resistors are attacked and the LEDs are placed on the breadboard using Ampere wires. After that, the Arduino is connected to the computer via the cable. Finally, the code is entered and defined through the Arduino software. The codes we enter into the system determine how our LEDs will flash. Thank you for listening to me.
Hello everyone, today I'm going to talk about static electricity. Electricity doesn't just work with batteries and wires. Static electricity is a great example of how electric charges move. Today I'll demonstrate this using my hair and a balloon. As you can see, when I rub the balloon against my hair, the balloon acquires static electricity, and as a result, it moves the pieces of paper. Thanks for listening. Bye guys.
We would like to express our heartfelt gratitude to our incredible partner schools for their inspiring collaboration, dedication, and teamwork throughout this journey.
Karabağlar Nevvar Salih İsgören Anatolian High School,
Yalvak Science High School, Sesim Sarpkaya Science High School,
Scoala Gimnaziala
NR.1,
Samsun İbrahim Tanrıverdi Social Sciences High School, Istituto Comprensivo Único di Borrelli, Agrupamento de Escolas de Penacova.
A huge thank you to all our amazing teachers and enthusiastic students who brought this project to life with their creativity, energy, and curiosity. Together, we broke down boundaries, made science fun, and created unforgettable memories.